Hey everyone, in this video we're looking at solutions. A solution is anytime you've got some water with something mixed in it, such as sodium chloride if you're looking at salt water, or hydrogen chloride if you have hydrochloric acid. We can quantify solutions in several different ways. We could talk about the volume of the solution that we have, we could talk about the number of moles or the number of particles that are dissolved in it, or we could talk about the molarity or the concentration. How concentrated are those particles in that solution? Can you see them in there? No, they're too small, you can't see them. So in this video, we're going to talk about the difference between molarity, moles, and volume. We're going to learn how to convert between each of those, and then we're going to take a look at a dilution, which is where you can take a solution of one concentration and dilute it down to a different concentration. So without further ado, let's jump to the whiteboard and get started. Cheers. Okay, don't ever do that in the lab. So in my diagram, I have those three quantities, the amount of solute, the volume, and the molarity. I'm going to talk about the differences between them and what they're really measuring here to start. So let's start with volume. Volume is just going to tell us how much space the liquid takes up. So say we have some solutions. Maybe we've got a sodium chloride solution that has sodiums and chlorines dissolved in it, or maybe we have hydrogens and chlorides dissolved, so we have hydrochloric acid, or whatever the solution is that we have. The volume is not telling us really the amount of those particles, the sodium, the chloride, etc. It's just telling us how much space does the liquid itself take up, which is going to be mostly water molecules. So in these beakers I have drawn here, I've got a small volume. In other words, the liquid takes up just about half of the beaker. And here I've got a relatively larger volume where the liquid takes up most of the beaker. But if you notice, neither diagram has any particles drawn. It's not telling us how much sodium, chloride, etc. that we would have in that beaker. It's just telling us how much space it takes up. Amount of solute, however, is going to tell us something very different. So in this diagram, we're going to look at sodium chloride or salt, and it's going to be dissolved in water. So we've got a sodium chloride solution. But when we're talking about the amount of solute or the moles of that solution, we're not looking at the liquid at all. And in this diagram that I have here, I've got the particles drawn in, which in this case are ions. We're going to have some positive sodium ions and some negative chlorine ions. But I don't have any liquid drawn because the amount of solute, or the number of moles, does not tell us the volume or the amount of total liquid we have. It's just going to tell us the amount of particles that we have that are in that water. So here in this first beaker, I've got 4 ions drawn in, and the second beaker, I've got 8 ions drawn in. So we would say that this first one has a smaller amount of particles, or in other words, fewer moles. And then the second one, we'd say it has a large amount of particles, or in other words, more moles than that first beaker. Now, of course, those particles aren't actually going to be just floating in midair. They're going to be dissolved in some water. I just didn't draw it in this diagram because amount of solute does not tell us the volume of water that those solutes are dissolved in. It just tells us the amount of them, or the number of particles of that solute that we have. Now hear me out on this. I have 4 ions drawn here and 8 ions drawn here, but in an actual solution of salt water, you're not going to have 4 ions, you're not going to have 8 ions, you're going to have billions and billions and billions. Actually, billions is not big enough. Billions would be like this number. We're talking about moles, and a mole is this number. It's a lot more, and I obviously can't draw that many particles, so we're just going to draw 4 ions and 8 ions for this example. And that's why we use a unit of mole, so that we're not always just writing everything in giant scientific notation and that sort of thing. So the amount of solute, or the moles, just tells us how many particles are dissolved in the solution. Next, we're going to look at molarity. And so molarity is going to be a little bit more complicated because it's a ratio. It's going to be a ratio of the moles of solute per liter of the solution. So if we had more moles, we'd have a greater molarity. Or if we had a smaller volume that those moles are dissolved in, then we would have a greater molarity as well. Let's take a look at a few diagrams to explore this. So here I've got 2 diagrams, 2 beakers. In the top one I have 8 ions drawn in, and in the bottom one I've got 4 ions drawn in. So I have twice as many ions in the top beaker, and I have half as many ions in the bottom beaker. However, I also have a different volume. I have twice the volume in the top beaker, and I have half of that volume in the bottom beaker. So in this case, we're going to have the same molarity. The ratio of the amount of particles that we have here per liter of water is going to be the same as it is in this bottom one. This one has twice the number of ions, but has twice the volume. Therefore, it's going to have the same molarity. So same molarity, but the top one has a greater number of moles and a greater volume. And the bottom one's going to have a smaller number of moles, or smaller number of particles, and a smaller volume as well. Let's compare a couple more here. I'm going to draw a second beaker. In this beaker, I've got the same volume, but I'm going to have a fewer number of particles drawn. So in this case, we have two examples where I've got the same volume. The amount of water, or the total amount of liquid, is going to be the same in both of these. But if you notice, I have fewer particles dissolved in this beaker on the top right. So we're going to have a different number of moles, and we're going to have a different molarity. In this case, we had fewer moles, but the same molarity. That's because our volume was smaller. But in this case, we've got the same volume in these two beakers, but we have fewer particles here than we do here. So in this beaker on the top right, we're going to have a smaller molarity. So just to summarize this, we've got a greater number of moles here because we have an actual greater number of particles. When we talk about moles, we're just talking about a way to count the particles. How many solute particles do we have dissolved here? And it's going to have a greater molarity. In other words, there's a greater number of moles of particles per liter of solution. And then on the right side there, we have fewer moles and then a smaller molarity. Finally, let's compare that top right and then bottom beaker. In that case, we've got the same number of moles. Take a look. We've got 4 ions in this beaker. We have 4 ions in this beaker. So the number of moles is going to be the same, even though their volumes are different and their molarities are different. They still have the same number of moles, because again, moles is just measuring the number of particles that we have. So in this bottom beaker, we've got a smaller volume, and we're going to have a greater molarity. So think about that. Molarity is just the concentration. We've got the same number of moles of particles here, but it's in a smaller volume or a smaller amount of liquid, therefore it's going to be more concentrated. Those ions are more concentrated together. And in that top right beaker, comparatively, we're going to have a greater volume, but we're going to have a smaller molarity. Same number of particles, but in a greater volume. Therefore, the molarity is smaller. Now that we have those things kind of defined and explored a little bit, let's take a look at how we're going to convert between these different quantities for a solution. There's a mathematical relationship that's going to compare these, and that's this equation right here. It's that molarity, which we represent with a capital M, equals the number of moles, which we represent with the lowercase n for number, divided by V for volume. Now, one thing you can do is memorize this equation, but I think there's actually an easier way to do all of this. So let's get rid of that, and we're going to use something called dimensional analysis. You may or may not have heard this term before, but dimensional analysis is a way to get to a final answer by making sure that units are going to divide out, so we're just left with that unit that we want. And that's a really useful tool, I think, for converting between moles, molarity, and volume. So I'm going to use one example solution and use that to calculate the volume, calculate amount of moles, and calculate molarity. I'm going to start by looking at what if we have the solution but we don't know what the volume is, and we're trying to calculate the volume. Then I'll show you how to calculate the moles if that's the thing that we didn't know, and then I'll show you how to calculate the molarity if that's the thing we didn't know. Either way though, you need to know 2 of these in order to calculate the third one. And if you know any 2 of them, you can always calculate the third one pretty easily. Let's take a look here that we're trying to find the volume of a solution. I'm going to make up a few numbers here. Let's say that we have 0.8 moles. We know what the moles of the solution are, it's 0.8 moles, and we're trying to find the volume. The other thing we need to know then is the molarity. Let's say that we have a solution that's 2 molar. Now, anytime we say something is 2 molar, we represent the molarity with a capital M, but that capital M for molarity just means moles per liter. So in your chemistry class, you're going to see this a lot, something that says 2 molar with a capital M. Anytime you see that capital M, always just think of it as moles per liter. That capital M molarity literally means moles per liter. Just change it into that and it'll make all these conversions really easy. So we have 0.8 moles. We've got 2 moles per liter. Okay, where did my 2 moles go? Moles are right here. So I'm going to need the 2 moles to go on the bottom or denominator of my fraction so that moles will divide out with moles here. And then it's per liter or per 1 liter. So I'm going to put 1 liter on the top. Moles are going to divide out, and I'm left with liters. So my answer is in liters, and I have 0.4 liters. So if I had a solution that I knew contained 0.8 moles of the solute, and that was a 2 molar solution, then I know that would have a volume of 0.4 liters. Also, apologies, there's something loud happening outside of the building. Nothing I can do about it. I don't have a soundproof room. All right, what if it's the amount of solute, or the number of moles that we don't know? So I'm going to use kind of the same numbers here. So let's say we had a 0.4 liter solution. I've got 0.4 liters in my beaker here, and I know that it's going to be a 2 molar solution, just like we looked at. I need to set this up kind of the same way. I'm going to start with 0.4 liters. I'm going to multiply by my molarity. In this case, I want the liters to divide out, so it's 2 moles per liter. So I need liters on the denominator, so it's over 1 liter. And that's 2 moles per liter, so 2 moles is going to be on the numerator, top of the fraction. The liters are going to divide out. I'm going to be left with 0.8 moles. So if I had 0.4 liters of solution, which is 400 milliliters of solution, and it was a 2 molar solution, I would know, easily can calculate that that's 0.8 moles of that sodium chloride. And that 0.8 moles, remember, that's a way that we can count the particles. If I want to know the exact number of particles, I would take 0.8 moles, multiply that by Avogadro's number, and that's going to give me some really big number that's going to be the number of sodium and chloride ions that are in that solution. Also, when I set this up, how did I know to start with 0.4 liters? Or in the previous one, how did I know to start with moles and not start with molarity? When I set these up, I never start with molarity. Molarity is a compound unit, it's moles per liter, and it's always going to be easier to start with just the single unit that you have. Start with liters or start with moles, and then use molarity as a conversion factor to find the unknown that you're looking for. All right, what if it's the molarity that you're trying to solve for? Now in this case, the molarity is moles per liter, so just use that to calculate it. Take the number of moles and divide by the liters, right? Moles divided by liters. Just set it up that way. So I have 0.8 moles of sodium chloride. I divide by the 0.4 liters of that I have, and that's going to give me 2 moles per liter. Now again, like I said, whenever you see 2 moles per liter, another way to write that is 2 molar with a capital M. So those mean the same thing. So again, that's how you can use dimensional analysis to convert between amount of solute or moles and volume and molarity for a solution. And I guess if you really wanted to, you could use that equation right there, but that's just another equation to memorize. Why not use dimensional analysis? Because you can use it for this, and you can use it for lots of other things throughout chemistry and physics and all other math-based science classes that you might encounter. All right, next let's take a look at something called dilutions. In a dilution, you're starting with a solution of some molarity, but you want to convert it to a smaller molarity. So let's say, for example, I've got 2 molar hydrochloric acid, but I'm doing a lab where I don't need 2 molar hydrochloric acid, I need 0.4 molar hydrochloric acid or some other molarity. I can use the solution still and just do a dilution on it, dilute it down to the molarity that I want. So let's take a look at what happens in that. I'm going to start off here again with 2 beakers, and I'm going to put some salt solution in them. In this left beaker, I've got 4 ions, and the right beaker, I've got 4 ions as well. How do I get from this to this? Well, I'm going to do that by doing a dilution. I'm going to do that by adding water, really adding distilled water. I'm not going to use tap water for this because tap water is going to have its own ions and impurities in it. I'm going to use deionized or distilled water to do this dilution. Notice what doesn't change though. In the left, I've got 4 ions. In the right, I still have 4 salt ions. Therefore, the number of moles of solute particles that I have did not change. In other words, my moles before the dilution equals my moles after the dilution. That's going to be key in just a moment. However, my volume did increase. Of course, I've got more liquid here on the right, and my molarity changed. In the left beaker, the ions are more concentrated, so I had a greater molarity. And in the right beaker, the ions are less concentrated, so I have a smaller molarity or smaller concentration. So let's call that beaker 1 and beaker 2. 1 is going to be before the dilution, 2 is after the dilution. And like I said, the amount of moles that I have in beaker 1, or moles sub 1, is equal to the moles that I have in beaker 2 after the dilution. And those aren't really 2 beakers, right? It's the same beaker because I just added water, but it's more of a before and an after. Beaker 1 is before, beaker 2 is after. Now we just saw earlier in the video that moles can be calculated by taking the molarity and the volume and multiplying them together. Molarity is moles per liter. Volume we often measure in liters. If you multiply moles per liter times liter, those liters would divide out and I'd be left with moles. So molarity times volume is the same thing as moles. I'm going to rewrite that moles per liter as just molar, and I'm going to rewrite liters as its variable, which is going to be V for volume. But again, this molarity times volume is the same thing as moles. So I can take molarity times volume before, or M1V1, and set that equal to molarity times volume afterward, which is going to be M2V2. Because again, molarity times volume is number of moles, molarity times volume is number of moles, and the number of moles, or the number of particles that I have before, equals the number of particles that I have after. This equation is super useful. We use it a lot. We use it for dilutions. We also use it in titrations, which is where you take an acid and you mix it with a base and you find out what the concentration of that acid was. So it just comes up a lot. It's a really important equation that we use, and it stems from the fact that the moles before equals the moles after. So that equation's all nice and good, but how do we actually do a dilution in the lab? So we're going to work it out here on the whiteboard, and then I'm going to show you how we would do it in the lab as well. So here's going to be our example that we're going to work through. Let's say that you have 2 molar hydrochloric acid in the lab, which we do right here. Here's our 2 molar hydrochloric acid. How would you prepare 100 milliliters of 0.4 molar hydrochloric acid? So I'm trying to do some experiment, and I need this hydrochloric acid, but it's too strong or too concentrated right here. My first step is to calculate how much of this I'm going to need for my target solution. So I'm going to start off with my equation here. M1V1 equals M2V2. Remember, our sub 1 means before and our sub 2 means after. So let's start off by substituting in any values that we know. So the before molarity is going to be 2 molar. I already have 2 molar solution of hydrochloric acid. That's going to be my before molarity, my molarity 1. Excuse me, let me get a drink real quick here. Again, lab safety is no joke. Actually, all jokes aside, I really thought about taking out those jokes from this because I don't want to make it seem like lab safety is not an important thing. It's actually really important. Don't ever pretend like you're drinking something in the lab. Don't do that, what I just did. What about V1? Well, I have a volume here, but that's the volume of solution that I want to prepare. I don't know how much solution I need to start with. So the V1 is going to be the variable that I'm going to be solving for. So I set that equal to M2V2. Our molarity 2, that's going to be our target molarity, our molarity after the dilution, and I'm wanting to prepare 0.4 molar hydrochloric acid. So 0.4 molar is my M2. And then my V2 is going to be the volume that I'm going to end up with, which in this case, I want to prepare 100 milliliters of that 0.4 molar hydrochloric acid. From there, I'm just going to solve for V1. So I'm going to divide by 2 molar on both sides. Those molarities are going to divide out on the left, and they're going to divide out on the right. I can leave it in milliliters here. A lot of times we have to convert milliliters to liters in some equations that we use. But in this case, milliliters did not have to divide out with liters anywhere else. So we can just leave it in milliliters. That's totally fine. So 0.4 times 100 divided by 2 is going to give us 20 milliliters. Okay, but what does that mean exactly? How do I go from this calculation that I did to preparing a 0.4 molar solution of hydrochloric acid? Before we get into that, let's summarize what we've done so far. We've done step 1, which is to calculate the volume of our starting solution. After we've done that calculation, our next step is going to be to add that 20 milliliters of 2 molar hydrochloric acid to a graduated cylinder. First, step 0 is to put on some goggles. Be right back. All right, much better. Now I have several pieces of labware here. I've got beakers, I've got Erlenmeyer flasks, I've got graduated cylinder, and I've got a volumetric flask. So a couple things: never measure any volume out in beakers or Erlenmeyer flasks. These are just for holding liquid. They're not for measuring. In fact, these values on here are just sort of like stamped on there. They don't actually measure out to make sure these values are accurate. So never measure anything in a beaker or an Erlenmeyer flask. I also have a graduated cylinder. Now the graduated cylinders are a lot better, a lot more precise. So we can use this to measure things. So graduated cylinders, great for measuring. The best thing for measuring out a volume is going to be called a volumetric flask. But the problem with the volumetric flask, or the limitation I should say, is that it only measures one volume. And in this case, I need to measure 20 milliliters. Well, this is a 100 milliliter volumetric flask. So I can't use this to measure 20 milliliters, but I can use a graduated cylinder to measure 20 milliliters. So we're going to use the graduated cylinder here. I'm going to take my hydrochloric acid, and I'm getting up to the 20. So I'm going to pour this in here until I get close to the 20, but I'm going to overshoot it if I keep going. I'm almost there. So I'm going to pour a little bit of this into a beaker. I'm not measuring in the beaker. I'm just going to use it to hold a little bit. And then I'll use a pipette here. Get some into my pipette. And then I'll add this in till we get as close as I can to 20 milliliters. All right, so I have my 20 milliliters of 2 molar hydrochloric acid in my graduated cylinder now. Now we're trying to make 100 milliliters of this, but we're not going to add 100 milliliters. If we added 100 milliliters of water, then we would be up to 120 milliliters of solution. But we want to have 100 milliliters total to get the target molarity. So we need to add 80. How'd I get 80? Well, I took 100 minus the 20 that I started with. We're going to add that to the graduated cylinder. Or we could do all of this in a volumetric flask, which is going to be the better way to go if you have a volumetric flask that measures the target volume, which I do in this case. Now, instead of measuring out 80 milliliters, what we're going to do is we're just going to fill the graduated cylinder of volumetric flask up to the 100 milliliter mark. So we're adding 80 milliliters of water, plus the 20 is going to mean that we're filling it up to the 100 milliliter mark. So I could do that by adding the water directly to here, but I'm going to, since I have it, use my volumetric flask. So I'll start by pouring this into the volumetric flask. So I've got my 20 milliliters in there, and then I need to fill this up to the single marking on there, which is going to be the 100 milliliter mark, because this is a 100 milliliter volumetric flask. I also have some drops of hydrochloric acid in here left, so I'm going to try to get some more of those drops this way as well. I'm going to do that till I get close to the line. I don't want to go over it, so then I'll take out the funnel and get the rest of the way like this. And now I have a 100 milliliter solution of 0.4 molar hydrochloric acid. I started with the 2 molar hydrochloric acid to do that. All right, back to the whiteboard. Let's summarize those other steps that we did. First, we calculated the volume of starting solution. Then we measured the starting volume. So we did that using a graduated cylinder. And then we added water to get to our target volume. We used distilled water in this case. It could be distilled or deionized, but not tap water. We could have added it directly to here and filled up to the 100 milliliter. But to get a little bit better, more precise result, we did that in the volumetric flask. And we added 80 milliliters of water to bring us to a total of 100 milliliters of solution. And like I said, that last step you can do with a graduated cylinder or a volumetric flask. Yeah, I should definitely edit out the part where I poured hydrochloric acid on my hand because I didn't use a funnel on the volumetric flask. But y'all, making videos is hard. And there's a lot to think about. Anyway, thanks for watching, and hopefully you have a better understanding of solutions, molarity, moles, and volume, as well as how to do dilution. And we'll see you in the next video.